Hi, Ali. I think it's probably about time we started the seminar. If you want to move to the next slide. Okay, good morning, everyone. My name's Mary Fletcher. I'm a professor in the Centre for Animal Science within QAFI, and it's my pleasure today to be the facilitator for the seminar for Ali Raza. Next slide, Ali. First, of course, I would want to do the acknowledgement of country. So I acknowledge the traditional owners and the custodianship of the lands on which we meet. I pay respect to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australia and the global society. Next slide, please. So firstly, a bit of housekeeping. Today's seminar will run from 12 till 1 o'clock. And after the presentation, we will hold a question and answer session. You're welcome to add your questions throughout the seminar, but please type them in the Q&A tab, not in the chat function, so that I can retrieve them and ask Ali the valuable questions at the end. So it's my pleasure to introduce Ali Raza. Ali is a Senior Research Fellow within our Centre of Animal Science, and he works in an area towards developing sustainable parasite control strategies. Ali graduated from the University of Agriculture in Faisalabad in Pakistan with a Doctor of Veterinary Medicine and a gold medal. He completed his PhD at Sorrow at the University of Queensland in 2017, and he uses next-gen technologies, including proteomics and whole genome sequencing, to determine biomarkers for host resistance to ecoparasites in cattle. Ali is one of our rising stars, and he works closely with partners from the government, industry, as well as national and international university. And of course, he's received several prestigious awards. So I'll leave it to Ali to introduce his seminar on the identification of super cattle with ectoparasite resistance. Over to you, Ali.
Thank you, Mary, for the kind introduction. I would also like to acknowledge the traditional owners and their custodianship of the lands on which we meet today. I pay my respect to their ancestors and their descendants. Today, I'll be going to talk about part of my research at QAFI, and as Mary mentioned, it's about discovering biomarkers for ectoparasite host resistance in cattle. According to the United Nations Food and Agriculture Organization, we will require 30% more food by 2030 and 50% by 2050. This rise is driven by a higher world population and by a change in the consumption pattern of people worldwide. The two major factors driving this transformation in food consumption will be rising incomes of these individuals and a trend towards increased urbanization. Similarly, the demand for animal-based protein will be increased by 70% by 2050. And currently, around 20% of animal and agricultural food production across the world is lost to the diseases. Therefore, to meet the daunting challenge, we need to secure profitable agricultural production. And one way to achieve this is by developing sustainable disease control strategies. According to the recent statistics released by Meat and Livestock Australia, the national cattle herd has reduced from 25.9 million in 2011 to 22.7 million in 2021. This emphasizes the importance of developing sustainable disease control strategies to improve for animal production. Buffalo flies and cattle ticks are the top two diseases in order of total cost to cattle producers, costing more than $250 million annually. As we can see that most of these losses occur due to the loss of production in both of these parasites. For example, the annual weight loss due to ticks in untreated clinically affected cattle averages about 15 kilograms a year. Both of these parasites are the targets of our research, and we focused on developing sustainable control strategies. I'll be presenting a part of this research on cattle ticks today. Just in case, if anyone is wondering why these parasites are so important and are ranked the #1 health problem. So you can see the cattle is infested with the buffalo flies. One buffalo fly bites more than 40 times a day to feed on the blood. And these buffalo flies can cause these type of lesions, as you can see in the next two photos. Then this cattle is infested with the ticks, and you can see one cattle can have thousands of ticks, and how much damage and irritation these can cause to the cattle. The cattle tick, Rhipicephalus microplus, is a hematophagous ectoparasite that affects around 80% of the global cattle population and leads to huge economic losses up to $30 billion. The economic losses occur due to the direct impact of cattle onto the of ticks onto the cattle by tick feeding, causing anemia and production losses. And the indirect effect losses occurs due to the transmission of tick-borne diseases and the treatment cost and the prevention cost associated with tick control. Let's dig deeper and see what these ticks do on the animal body. I hope the video is playing well, and you can see the ticks are and different developmental stages of these ticks are half buried into the cattle's skin. And they continuously feed on cattle blood for up to 3 weeks. And then you can imagine how much irritation and damage they can cause to the animal and animal skin. As the animals suffer due to this feeding activity, I'm sure that the ticks must be feeling something like that. Being Australian, we like to have our version of everything more than the rest of the world. Thus, the cattle tick is cattle tick is called as or Australis in Australia, although there is still a debate about the blue gene. The cattle tick is prevalent in eastern and northern areas of Queensland, Northern Territory, and parts of Western Australia. However, climate changes will likely expand suitable tick habitat further south within high rainfall regions. Rhipicephalus australis is a one-host tick, which means all of its 3 feeding stages, larvae, nymphs, and adults, remain on the one host till the adult females drop off and lay eggs. The parasitic phase of the life cycle is around about 3 weeks, whereas the non-parasitic phase can be up to 9 months, but it depends heavily on the environmental conditions. Tick control has heavily relied on the use of apericidal drugs. However, the development of drug resistance and the contamination of food products and the environment are the limiting factors for apericidal use. The development of an effective anti-tick vaccine hasn't seen significant success. For example, BM86 was the only commercialized vaccine in the country in the 1990s, but the requirement for regular boosters every few months limited commercial uptake, and the vaccine was discontinued. After that, there is no new Australian-ready vaccine has become commercially available since then. And the research to identify novel vaccine candidates that induce longer lasting and more effective immunity remains ongoing. It is now well known that the increasing Bos indicus content is associated with higher resistance to tick attachment, which has been linked with the physical and immune factors. However, there is substantial variation in resistance within Bos indicus strain. Therefore, the question is, how do we know which cattle will carry a lower tick burden in the future, especially when they all eat the same? For this, cattle phenotyping methods are required to select resistant cattle for selective breeding. The currently suggested methods to determine the cattle phenotype for tick resistance includes hematological analysis, skin hypersensitivity testing, and artificial tick challenge, followed by tick scoring or tick counts. However, each of these methods comes with the limitations and has limited application. For example, hematological analysis was developed for blood-feeding nematodes in sheep and hasn't been validated for pigs. Secondly, multi-parasite infection will result in different signatures of response, and even if successful, it will require a portable blood analyzer to perform the test. In the skin hypersensitivity, the cutaneous hypersensitive response time of cattle to unfed larval extract is measured. This larval extract is injected subcutaneously or intravenously onto the cattle ear. This method is time-consuming, as the response time varies from minutes to hours and depends on different individuals. It requires technical expertise to inject the extract and evaluate the readings. There is also a need to validate the reaction time in other breeds and a detection score tool to enable the interpretation of the results may be required because it works with the algorithms and logistical patterns. And lastly, the artificial tick challenge is the most commonly used method. Cattle are exposed to the tick larvae in different ways. For example, as you can see in this tick bag test, and then the adult ticks are counted after 18 to 21 days. Other methods include pouring the tick larvae on the back of the cattle, which is commonly practiced here in Australia. However, in the field, farmers let the cattle to be exposed to natural infestation and then use a tick scoring method to estimate the number of ticks on individual cattle for phenotyping and selective breeding. Thus, this requires long time. For example, at least 1 or 2 seasons are required to measure to determine the phenotypes of the cattle. To develop new phenotyping methods, it is essential to understand the mechanisms associated with tick resistance. This figure shows a nice summary of gene expression patterns and immunological profiles commonly associated with tick susceptible cattle, the upper photograph, and compared to the tick resistant, the cattle at the bottom. For example, the resistant cattle carried a higher number of eosinophils, whereas the susceptible cattle have more neutrophils. However, there was variation in the experimental designs across these studies. For example, most of the studies did not use true live cattle. The cattle previously infested with ticks were cleared of ticks with the drugs before including in the experiment. Thus, we cannot say that these changes in the immune response cells or immune response overall was the true representation of the tick infestation. Several previous papers on bovine immune parameters contributing to tick resistance discussed findings across DNA, RNA, protein, cellular entity level. However, gene expression often does not correlate well with the protein expression. And since proteins are major functional determinants of the cells, thus a large-scale study of the proteomes to investigate the differences between tick-resistant and susceptible cattle would provide useful information at the protein level. Recently, we reported that tick-resistant cattle, Santa Gertrudis breed cattle, carried several proteins at significantly higher abundance, which were associated with immune response. That may enable the tick-resistant cattle to develop an effective protective immune response when exposed to the tick larvae or the tick infestation. This highlights the potential of genetic selection of post-resistance as a method of choice for the non-chemical control of ticks. Therefore, in this current project, we selected Brangus breed to validate our previous findings. And for this purpose, 35 Brangus steers were repeatedly infested with 10,000 larvae of the non-field resistant strains of cattle tick for up to 13 weeks. Animals were scored for tick burden by estimating the tick numbers, by visualizing the ticks at the base of the tail and between the hind legs, as well as palpating with the palm of the hand on the one side of the cattle. This is the timeline of the experimental plan. Blood and skin samples were collected from animals on day 0, and then the animals were infested the next day. The day 0 samples were called as naive samples, The tick larvae were poured down the back of the cattle up to week 12. Animals were stored from the third week following the first infestation up to week 15. Samples were collected at different time points. As we mentioned, the pre-infestation was day 0 and the post-infestation, as you can see these square boxes. The samples used in this current experiment which I'm presenting today were from the pre-infestation, day 0, early infestation, which were collected 6 hours after the first infestation on day 1, and the third sampling time point was after prolonged exposure to ticks, that is 105 days post infestation. The scale used for tick scoring ranged from 1 to 5, with a score of 1 representing the least number of ticks, and a score of 5 representing the most number of ticks. At the end of the trial, the animals were segregated into 3 groups based on their mean tick score, as indicated in this graph. And 6 animals from the 2 extremes were selected for the further processing. To determine the relative abundance of serum and skin chlorine in both groups of cattle, a mass spectrometry was used, and the SWOT method was applied for the candidate proteomics. In a SWOT analysis following initial sample preparation, an ion library containing 2-dimensional molecular signature is generated by analyzing representative samples by LC-MS using information-dependent analysis acquisition mode. This library then represents all the ions that are present in the sample and acts as the database onto which the SWOT reads are then mapped. Once mapped to the ion library using specialized bioinformatics software, this SWOT data uses a quantification of every molecule in the ion library at the MS level. First, I will present the results from the serum samples, and these samples were used to determine the systemic response to tick infestation. Initially, we identified 220 proteins from the library pool, and based on 1% false discovery rate cutoff, 167 proteins were used in the SWOT analysis to measure the relative abundance of each protein within individual samples. The principal component analysis provided an overview of the deviation of protein abundance in each cattle within the groups. This PCA showed partial separation and clustering of all 3 groups in resistant cattle. With samples from early exposure, the blue dots were clustered in between the naive, the light sky blue dots, and the resistant red dots groups. Whereas the samples from susceptible cattle following prolonged exposure were separated from susceptible naive, the yellow dots, and early exposure black dots, which were clustered together. These volcano plots show the differentially abundant proteins in tick-resistant cattle on the left-hand side and the susceptible on the right, following 6-hour exposure to the tick larvae. The x-axis represents log 2-fold values with a positive scale, indicating the proteins with a higher abundance after larvae exposure, and a negative scale for the proteins with lower abundance. The x-axis is the log 10 of the adjusted p-values, and the cutoff for the p-value was less than 10⁻⁵. The colored dots indicate different fold change. For example, the blue indicates plus values, and the red indicates the negative values, and the purple dot indicates the log 2-fold change less than 0.2. The resistant cattle were more responsive to the tick infestation, as indicated by the higher number of differentially abundant proteins when compared to the susceptible cattle. However, most of the proteins in susceptible cattle showed changes, slight changes, meaning their log 2-fold changes values were less than 0.3. Interestingly, the abundance of 29 proteins decreased in response to tick infestation in resistant cattle. This may be explained in 2 ways. There could be immunosuppression, but if this was due to immunosuppression effect, This should also be evident in susceptible cattle. Another explanation could be that this reduction in protein abundance was due to the consumption of these immune-related proteins in larval rejection. I would mention here that among these 29 proteins, most of the proteins were related to immune response. For example, 5 of these proteins were complement factors, and there were other immune-associated proteins. Another possible explanation could be that these cattle were able to transmigrate the immune response-related protein to the local fixed bite site for developing an effective immune response. The protein-protein interaction network ensured that differentially abundant proteins in resistant cattle were clustered into 3 distinct clusters, as we can see on the left-hand side, whereas only one cluster was observed in susceptible cattle. That was probably most of the proteins was only showed lower loss filtration value. The functional enrichment showed that differentially abundant proteins in both the groups of cattle were enriched in biological process proteins associated with complement activation, leukocyte-mediated immunity, and regulation of immune response. However, more proteins associated with these biological processes were reduced in the systemic circulation in resistant cattle. In addition, the resistant cattle also showed modulation of regulation of wound healing, inflammatory response, and blood coagulation, which were not observed in susceptible cattle. And in these biological processes, there were proteins whose abundance was also increased. So it means that these processes were in resistant cattle. Both groups were more responsive to tick infestation following prolonged exposure to tick larvae. As we can see, the number of differentially abundant proteins were quite relevant in both comparisons. Again, we can see that the abundance of most of the proteins was decreased after persistent infestation, and this time it happened in both groups. However, the susceptible cattle showed a greater number of proteins at significantly higher abundance as compared to the resistant cattle. And the functional enrichment of these differentially abundant proteins following prolonged exposure showed that the immune-related biological processes were modulated in both groups of cattle. For example, leukocyte-mediated immunity, complement activation, inflammatory response, and wound healing. In addition, the susceptible cattle also showed a reduced abundance of proteins associated with adaptive immune response, iron transport, and fibrinolysis. This dot plot further explains the differences between resistant and susceptible cattle following peak exposure when compared to the randomized groups. For example, wound healing and blood coagulation processes were active in resistant cattle at both early and prolonged exposure, as well as hemostasis, whereas these processes were active in susceptible cattle only after prolonged exposure. So that could be a biological response of the cattle due to persistent heavy infestation of the tick. Then we moved on processing the skin samples to determine the cutaneous response to tick infestation in both of these groups of cattle. Initially, we identified 617 proteins from the protein panel search, and based on 1% quality study date, we used 333 proteins in the SWOT analysis. The clustering analysis of protein abundance in individual animals showed that there was less variation, which perhaps was due to the presence of highly abundant conserved proteins in the skin, such as keratins and collagen. These volcano plots show the differentially abundant proteins in tick-resistant cattle on the left-hand side and the tick-susceptible cattle on the right-hand, following 6 hours to the tick larvae. But here we see again that resistant cattle are more responsive to tick infestation, as indicated by the higher number of differentially abundant proteins when compared to the susceptible cattle. And in the skin samples, the abundance of 62 proteins was increased and resistant cattle in response to taking prescription of 6 hours, as compared to 50 proteins in susceptible cattle. The protein-protein interaction networking identified that there were a greater number of fragments in the structural protein cluster as compared to susceptible cattle and the cluster containing proteins associated with blood coagulation and wound healing was only observed in resistant cattle. Functional enrichment showed that the differentially abundant proteins were enriched in extracellular matrix protein proteins in both big groups. Whereas the differentially abundant proteins, mostly at higher abundance in resistant cattle, were also enriched in platelet aggregation, blood coagulation, and wound healing, which were not observed in susceptible cattle. On the other hand, the differentially abundant proteins in susceptible cattle were enriched in skin morphogenesis. In response to prolonged heat exposure, the skin proteomics showed identical responses in both groups. As we can see in this Venn diagram, that 66 proteins were common in both the groups after prolonged exposure in skin samples when these were compared to the relevant live baseline samples. And the abundance of most of these proteins was increased in both the groups. As you can see, 43 and 44. The resistant cattle still showed a higher number of proteins whose abundance was increased, as you can see the number is 28. Interestingly, differentially abundant proteins in both groups were enriched in blood coagulation, platelet aggregation, and wound healing. These were the processes which were significantly enriched in resistant cattle at an time exposure, but these are significantly enriched in both groups at prolonged thick infestation in the skin sample. Whereas the extracellular matrix organization growth term was highly enriched in resistant cattle as compared to susceptible cattle. And the susceptible cattle showed some unique biological process growth terms, including response to stress, negative regulation of coagulation, and regulation of cellular response to oxidative stress. This indicates that the heavy heat burden might be in these biological processes and activating some of the processes which are favorable for heat feeding, for example, negative regulation of blood coagulation. This bar graph shows the unique proteins in the skin of both groups, in the skin samples of both the groups at different time points compared to the relevant naive samples. Interestingly, complement factors C3 and T4A were detected in the skin samples of resistant cattle at both time points, which supports the hypothesis that immune-related proteins were transmigrated from systemic circulation to the skin by site in response to larval infestation, and this may play a significant role in larval injection. It is, however, worth mentioning that these two complement factors were detected in the presence of highly abundant keratins and collagen, which suggests that there might be more immune-related proteins present locally adapted by the site. Then the next question was whether tick-resistant cattle carry different proteins before and tick exposure than tick-susceptible cattle. For that, to answer this question, we compared the samples from naive, resistant, and susceptible with naive samples. The results showed that the number of proteins at higher abundance was 3 times higher in tick-resistant cattle, tick-resistant naive cattle without any exposure to ticks. And most of these proteins were involved in immune response. For example, 8 of these proteins were complement factors, and there were proteins which were associated with other protective mechanisms. For example, in this protein-protein interaction network, it was shown that the differentially abundant proteins were clustered into 3 clusters. It was associated with complement activation, innate immune response, leukocyte-mediated immunity. The second cluster was associated with regulation of activation of membrane attacks on plaque and regulation of phagocytosis. and the third cluster was associated with that coagulation. As we can see from the color of this hollow color based on the local flow chain, most of these proteins were higher in resistant cattle, as I have explained in the previous slide. And all of these processes were highly active in resistant cattle even before the. This is the complement activation pathway. The red color indicates the proteins with higher, the red color indicates the proteins with higher abundance, and the green color represents the proteins with lower abundance. The proteins at higher abundance in resistant naive cattle are complement system activation components, whereas the two proteins that are at lower abundance are the inhibiting factors in complement system. This indicates that the complement activation pathway is already there before the tick infestation in resistant naive cattle. And this has previously been suggested that and reported that the complement factors and the complement pathways play a significant role in early larval rejection. Finally, the findings of the mass spectrometry were confirmed with the detection of variations in the protein level between the groups using muchly available ELISA kits. As we can see, these graphs show that the resistant naive cattle had significantly higher levels of alpha-1 glycoprotein and glycoprotein. And this difference was also observed for the alpha-1 glycoprotein between the two groups after the infestation. This verified the findings of the mass spectrometry and also highlighted the potential of using such type of methods such as ELISA kits in the field to validate and to determine and to detect these biomarker or these proteins in the biomarker. So to summarize, these findings showed that the host responses to tick infestation at both systemic and cutaneous levels were detectable as early as 6 hours after tick infestation. And this is the first observation because the previously published studies have reported the response in after 24 hours. The tick-resistant cattle rapidly responded to early exposure to tick larvae with modulation of inflammatory response, wound healing, and blood coagulation responses. In addition, the skin proteomics data showed that the resistant cattle effectively managed to mobilize the immune-related proteins to skin, the tick-host interaction by site, while along with the extracellular matrix proteins, which were associated with maintenance of skin integrity and wound healing, increased the likelihood of early larval rejection. On the other hand, susceptible cattle developed some of these protective mechanisms only after prolonged exposure to the ticks, along with mechanisms facilitating tick feeding, such as fibrinolysis. Previously in the literature, this has been reported that the ticks carry bioactive compound molecules in their saliva, which suppress the host immunity and other protective mechanisms such as wound healing, blood coagulation, and inflammatory responses. Therefore, presence of such type of biological processes without an tick exposure in a certain group of cattle would help them to develop an early protective response that can lead to early larval rejection, and that ultimately will result in slow tick killing. In addition, the tick-resistant naive cattle showed a strong immune response before tick exposure, which was evident from the presence of highly abundant proteins involved in complement activation, leukocyte-mediated immunity, membrane-attack complex, and phagocytosis, thus enabling these group of cattle to develop a protective response upon tick exposure, which was also evident from the responses to the first exposure to tick larvae after 6 hours post-infestation. Therefore, the immune response-related proteins, such as Complement 4A, alpha-1 it's a glycoprotein and convertin could be used as potential biomarkers in naive cattle, and the CD4-like molecule, vitamin D binding protein, and the alpha-1 it's a glycoprotein could be used as potential biomarkers in case of if the animals are infested in the field. So these proteins show higher abundance in the distant group following peak exposure. So these proteins, in addition to we can include some other complement factors, could be used as a panel of potential biomarkers associated with peak resistance. The next phase of this research is to validate these findings in the field, testing on different animals from different types and ideally from different fields, which is still in progress. Before I finish, I would like to acknowledge my colleague in the animal biotechnology group who helped me during this research project. And the animal biotechnology group is led by Professor Ala Tabor. Our project leads, Professor Ala Tabor and Dr. Peter Jean. And the Punjara Hills research staff, Alison and Tom, for the wonderful help during this tick infestation trial. Our national and international collaborators and of course our funding partners, without their support, this research was not possible. And I hope that we will continue receiving this funding from these funding partners and others. And lastly, this mob of volunteers who generously offered their blood and a piece of skin for this study, except this fellow who refused to donate his blood on day 2, and we had to exclude him from the study. And it turned out that this was the most susceptible fellow among all these 35 volunteers. So if you have any questions, please, you're welcome to ask. Thank you.
Okay. Thank you, Ali. We had at least one comment that someone was having trouble understanding with the audio content. I'll just make it clear to everyone that the seminars are recorded, and hopefully if there's any mix up in the sound, they can clear that up before it's posted online. Remind you also that you can put your questions and answers in the function below, or if you want to raise your hand, I can turn you on to actually ask the question directly. So please put your questions in there. So to start the ball rolling, so Ali, you were talking mainly about the resistance to ticks. Do you believe that these traits, if you can select for the cattle, would be inheritable?
The heritability for tick resistance was previously reported around 34 to 40%, and like there is a good potential of being these traits heritable.
Okay, so you think there's a potential to actually produce these super cattle?
Yes, we do hope so, and the last phase of the project will be to determine the genomic values for associated with these proteins, and then we can probably implement those and onto the database and see if they are and calculate the heritability of these proteins.
Okay, we don't seem to be collecting any questions from anyone, so please, your last chance. One question, this, as everyone may know, this is actually Honours Week, and the possibility of other people, younger researchers joining your team. Do you have opportunities going for more research?
Yeah, there is a question, Mary Campana.
Oh yes, actually, I did actually see one come up. Can you see the question?
Yeah, she said the cyclet 15 comes up as differently expressed between the tick resistant and susceptible. Have you investigated this gene any further? Yes, I'm looking into it, Hannah. This cyclet 15 was significantly decreased in susceptible cattle in response to peak exposure, and the log fold change was quite high. About, I think it was 5 or 7, and the manuscript will be soon submitted for the publication, and there will be more around discussion around these proteins. Most of the aglax are like immunoglobulin binding proteins.
Okay, Hannah, does that answer your question? Okay, I think we might just wrap it up there, Ali, if that's okay. If you want to move on to the next slide. Okay, so it reminds me to actually thank Ali for his talk and his exciting research. Sorry, someone's got a lot. Okay, Hannah just acknowledged your reply, so she's happy. Since nobody else has given us any questions, we'll wrap it up and say, look, these science seminars, coffee science seminars occur every week, so hopefully everyone signed up on the seminar invitation list. You can actually join and so you get notified every week from the coffee links. And you can also give us feedback by scanning the QR code to the right. So that will help us shape our seminars for the future. So next week's seminar, as shown on the screen, is a seminar from Prof. Mike Gidley, who's currently our Centre Director for the Centre of Nutrition and Food Sciences. So Mike is leaving us soon, so this may be your final chance to listen to one of his seminars, and his seminar is entitled Nutrition and Food Sciences for Futures. Okay, and so it's a thank you slide, and yes, a reminder that the talks are recorded, so you can actually listen to them again to your heart's content, or listen to any other previous seminar that's also been recorded on that website. And we must actually thank the Science Seminar Committee, coordinated by Craig Hardner. So if you actually want to be involved in giving future talks, feel free to email Craig. He's always looking for willing volunteers, or if you have any suggestions or other people to give science seminars. So thank you again, Ali. I think that's our final slide.
Yep.
Okay, thanks, Ali.
Thank you. Bye.